Okay, the white handout here. Look. So I'm hoping that the fact that I gave you a white handout and then I gave you a sheet protector for the white handout will be sufficient indication that this is an important thing to keep and not lose. Look at me. In my opinion, this is the side I'm going to be using primarily. You'll notice that the box at the top is repeated on both sides. The large piece of information here at the bottom on one side, that's like a lot of extra examples for people who kind of struggle to understand the initial box. My hope is you'll understand what we're talking about here. You won't even need this. Like, I don't ever look here. I just look at the top. So that's why I repeated that top portion on this side, because that's the most important piece. This side also has some notes that I've given you previously in homework packets. I just put them all together here because once you get better and better at understanding something, you don't need so many notes any longer. Like, I feel like this is enough to summarize what we have learned so far, plus what we will learn pretty much the rest of this unit, is this one sheet right here. Like, if this makes sense to you, you should be all set for the test, I believe. I might have to check and make sure I'm not forgetting something, but questions. So hence the importance of this. The purple packet is your homework. It's not really, I don't think it'll be too bad tonight. It's kind of like the gold and the green. We'll talk through part of the purple today, and then you'll finish it as homework. And it's a lot of repetition again. The whole goal here is for you to get very comfortable with how these three graphs are related to each other. Position, so trying to figure out how position relates to velocity, how velocity relates to acceleration. So we're looking at those three. I don't think I used a word last time that I need to introduce you to. Just nod if this sounds familiar. Did we not last time talk about how to do this on your calculator right here? We talked about that? Okay, so we've seen that. This mathematically is known as a derivative. I don't think I used that word. Okay, so this is known as a derivative, but be a little careful. The D does not stand for derivative. A derivative is a division. What you're doing is a comparison. The D stands for infinitesimal difference. So when I write a D and I put like position next to it, I'm stating that I'm going to go find how different are two positions that are right next to each other. Like, how different are those positions? I'm going to compare that to how different the times are for those same two positions. So the D does not stand for derivative. The D stands for difference. I'm comparing how different are two positions as opposed to those two times that correspond to those two positions. And it really is division. It's really this difference divided by this difference. And that entire operation is known as a derivative. So the D isn't derivative, the D is infinitesimal difference. The entire division, that's a derivative. Question? Okay, what we did study last time is that these three are related, position, velocity, and acceleration, by the fact that if I find the derivative of position, if I calculate the rate at which position is changing, I find the derivative, I found velocity. That was in your gold packet. It said the derivative of position, come on, pen. The derivative of position is the same thing as velocity. And then the derivative of velocity is acceleration. And then there was also a note in the gold packet that said the second derivative of position, so I take two derivatives, that's also accelerations. Questions? So today, oh yeah, please.
How do you take two derivatives of something?
Basically, all you do is I take the derivative of position, 3 points for Andrea. I get velocity. If I then take the derivative of velocity, I'm going to get acceleration. So that's equivalent to saying I took two derivatives of position.
Okay.
Somebody else? Cool. All right. So today, it's just more work understanding how those three functions relate to each other. One thing I'd like to do to start out with is point out that as a student, I found it really annoying to have to look at a page like this and then think, oh, wait a minute, I need to look at the graph. So I have to flip back to here, look at the graph, flip back. So an easy way to fix that problem was for me to simply give you, Sarah's got it, the very last page, just rip it off. I really hate busy work, so I am trying as best I can to make it easier for you whenever possible.
I don't think mine has one, because this is already here.
It's probably the one I ripped off already. So,
Thank you.
convenient. Sorry about that.
You're good.
I wish I could separate the answers as well, but it does get a little unmanageable, too many handouts and things, so sorry to have to flip that a little bit. Anyway, the other thing I want to do is I want to show you how I found these times, just so you are familiar with how to find them yourself. But once we find them, you can just write them down. Like, I've never had anyone ever struggle on a test because they couldn't figure out how to use the calculator. Using the calculator tends to be I show you once or twice and you're all set. So I'll just show you, you write them down, then you don't have to use your calculator on this entire assignment. You can just use what's written down. For example, these are the graphs, and I want to find where this red graph acceleration is crossing the x-axis. That's called finding the zero of that function. So the way I do that is I go second. You should have done this in some previous class, but in case you've forgotten. Trace, so second trace. Then you simply choose 0 right here. So 2. They're now asking for the left bound. They want this. That means I need to put the cursor on the acceleration curve. So I'm on the wrong curve because I'm sitting here on position. So I use the up and down arrow right here. The up and down arrow, I just keep moving it until I can find that I'm on the acceleration curve. So right there. Now I'm on acceleration. I can see that I'm on acceleration. It's asking for the left bound. So I'm going to move my cursor until I get to the left of where the 0 is located. Then I press enter. It's asking for the right bound. So I move my cursor until I'm on the right side of the 0. Press enter. It says guess. That means put your cursor near the location of the 0. Oh, please, sorry.
What window are you on? Is my graph like?
Oh, gotcha. Let's back up. My bad. Sorry, 2 points. What I did, so I cheated on you on that one. That's my bad. I knew I wanted to find this. And so I zoomed in from like 0 to 1, just to see it a little bit closer. No, sorry, I didn't notice sooner. Guess just means put the cursor near the 0. I'm close enough, so I can hit enter. And then it calculates the 0. Just make sure you see the word 0 right here. If it doesn't say 0, then you've done something wrong. So just go like this. You need to go through it again. I don't mind. So I'm on the graph. I go second. It's actually the calculate menu, but it's the trace button. I want to choose 0. Nick very helpfully pointed out that in my videos, I don't always point with the marker, so I'm hoping this will help. Because I noticed here, Nick, that like when I go like this, the arrow does show up.
Yeah,
So I'm hoping that shows up in the video. So, for those of you that have watched at home, if you see other things that I can do different, don't hesitate to tell me. My whole point is to make it as helpful as I can. So, so I choose 0. Ainsley's agreeing. It's like Mr. Smith says, "Look at this." I'm like, what are we even looking at? So, now it says left bound. So I need the cursor to be on acceleration. So I'm on the wrong graph. So up and down arrow will move me to the correct graph. So now I'm on acceleration. I have to be to the left of the 0. So move over. Press enter. Now I need to move to the right of the 0. Press enter. Guess means just be near the 0. If you make your left and right bounds close, you're close enough. You can just press enter. And then make sure that it says 0 right there. Make sure it says 0. So, question, please, comments.
Sorry, mine says guess instead of 0.
Oh, so the guess is saying put the cursor near the location of the 0,
Okay.
then press enter one more time.
Okay.
Try that. Tell me what happens.
Even if one of those coordinates is one that already goes to the left or right down?
Yeah, it's totally okay.
Okay. All
Tell me what happens.
right. Okay, yeah, I got that.
Got it? Perfect. 2 points. Anyone else? Cool. So basically, on the handout now that you tore out, feel free to just write that in, the time for that spot, so you don't have to keep calculating it. And I don't see the value in going through that exercise over and over again. So you can go ahead and write in these times as well. This time here is found slightly differently because what I did is I found where the acceleration graph had a minimum. It's exactly the same process. The only difference is on your calculator, when you say second calculate, you're going to choose minimum instead. Otherwise, exact same process, so I don't really feel like you need to practice that. It's really not hard. I've never ever had a student who struggled with that. So just write those down. We'll just use those numbers. So there's a purple one on your desk. Question? Oh, please, Cameron.
So we're just trying to find the minimum and when it hits the 0 or the
Right.
x-intercept.
And you'll see why I'm finding those in a minute. But the key times we are interested in is the 0 here, the 0 here, 0 here, and then we also have some interest in where the acceleration is hitting a relative minimum. So, please.
How come you're not interested in the far right road?
Way over here.
Yeah, on the blue line.
Only because the questions in this packet didn't concern that. Yeah, there's 3 points for Nick. This point has significance in the fact that this is the moment, like we talked before about how this particular particle went left for quite a while, went all the way to like -155, then came back. This is the exact time when the particle is once again back here at the origin. It just didn't show up in any of the questions in this packet. Good question. So, okay, here we go. Number 1. And you'll find this packet to be somewhat repetitive. That's not meant to be annoying, that's meant to be helpful. It's just that I'm trying to help you see how the different graphs relate to each other, so things do feel a bit repetitive. It says use the position graph to determine, the other thing is the questions work themselves from left to right. So as you're reading through the packet, if you go in order, you're just working across the graph. Use the position graph to determine that the particle's position is decreasing from time equals 0 until what time? This is not meant to be a hard question, but I think you learn far better if you're doing the thinking rather than just listening. So I think it's an easy question, but talk if you'd like. Raise your hand and tell me, what should I write here? What goes in this blank right here? Talk to each other, raise your hand. So it says use the position graph. So position is the blue one. To determine that the particle's position is decreasing from time equals 0 until what time? So hands up, what time goes here? Hey everybody. Oh, remember in this class, keep your hands up. In this class, it doesn't matter how many times you're wrong. So I would far prefer that even if you're like, I'm not really sure, that you raise your hand. If I call on you and it's incorrect, it doesn't matter. It's the act of you trying and then figuring out what went wrong that will help you learn. If all you ever do is listen, you won't learn nearly as well. So just, if you're, any idea, just raise your hand. Ainsley?
4.840.
So what I notice is these y-coordinates on the blue graph, the y-coordinates tell me where the particle is located. So the particle is having a position that is increasingly negative, meaning it is moving to the left until I get right here. Those position values, those y-coordinates, stop going more and more negative. They start to become less and less negative. That's the exact moment when the particle stops going left and starts moving back to the right. That is exactly the time when the position graph stops decreasing. So you'll write down 4.848. Show me your hands if you knew that. 2 points, 3 for Ainsley. Question. Okay, keep going. Here's how the whole packet will go. Is like I'm just trying to show you how things correspond to one another. So it says, therefore, the velocity graph, we talked about this last time. When the particle is going to the left, so when the position is decreasing, that means my position is becoming more and more negative. As this position graph goes down, my position is becoming more and more negative. At that exact same time period, my velocity must be negative, because I cannot go left unless my velocity is negative. So look here, and that's why I gave you all 3 graphs so you can see how they correspond. So don't just answer the questions. Make sure you're paying attention to how the graphs correspond to one another. And one other warning, I gave this earlier in the year, but sometimes when we have days that seem easy, the warning gets forgotten. Don't ever be on your cell phone during class. The deal is, first test, 80% of your grade, but you only get to retake if I have no recollection of you ever being on your cell phone. If you're on your cell phone, you come to me and say, hey, I only got 5 right out of 25. What do? I'm like, counseling's down the hall. So that sounds harsh, but there's no way to come back from it. Like, look at me. If you're with me the whole time, like as we're discussing, and I get that some days it seems easy, it happens. But if you're with me the whole time and then the test is a disaster, then I'm going to say, hey, you're committed to doing well. It's just something went wrong. Let's figure out what it was. But if you're not with me, I can't help you recover. Like you just lost all that time. So anyway. So, look. The entire time that position was decreasing, notice how the velocity had y-coordinates that were always negative. They have to match up. And you must see how they match up. On a future test, you're not going to get all three. You're going to get one of them. And then you have to answer the same questions by looking at one of the graphs. So you have to know how they correspond to each other. Please.
How do you know if the velocity is like slowing down?
That you have to pay attention to the numbers themselves. So what I noticed, Kayla, is right here at time 1, my velocity is about, I don't know, negative 20. That means my speed is 20. So I'm going 20 meters per second to the left. At time 2, my velocity is negative 35. So I'm still going left, but now I'm going 35 meters per second to the left. So along here, I am speeding up. Right here, I stop speeding up because now my velocity values become less negative. So my speed goes like from negative 60, so my speed goes from like 60 to 40 to 20. That's my speed, because the speed does not include, speed is the absolute value of the velocity. I'm not sure I helped at all.
Yeah.
2 more points. Questions? Cool. All right, so the velocity graph is negative for that exact same time period. I also have a chart over here to help you. Okay, the chart summarizes what I'm saying. And I have to give credit to a student. I didn't come up with the chart. The first year I taught calculus, I went through all these concepts and showed everyone how things related. One of my students figured out, hey, if I make this little memory aid, it's a lot easier to solve all these questions that they keep giving me. And all she did was notice that, hey, when the position graph is decreasing, all the y-coordinates of the velocity graph have to be negative. And she just put it in a chart. So we named the chart after her. We put a sign on the wall. It's called Danika's chart. So her name was Danika, right? Questions? Cool. Keep going. We already talked about this one. Therefore, the particle is moving to the left. From time equals 0 to time equal 4.848. And again, what you should be paying attention to in this class is not that you can write down the answer, it's that you can actually look at it and go, yeah, that makes sense to me. Like, pay attention to how you feel. If you feel something isn't making sense, just talk. Next, please.
On A, how do you know if you put negative or decreasing? Like, when do you use the different ones?
Gotcha.
Some of them are decreasing and more negative.
So the way I read this sequence of thoughts is, and what it's trying to prompt you to do is see how they correspond. So it says, use the position graph to determine that the particle's position is decreasing. So there they're telling us to look there. So we figured out the position is decreasing from here all the way to here. So now the A and the B are going to talk about how other graphs correspond to that. So that's where the chart can give you the clue. You can say, okay, I get it now. I'm supposed to make sure I understand that when position is going down, my velocity has to have negative y-coordinates. Did that answer your question?
Yeah.
2 points, please.
I'm still kind of confused why you put left instead of like right.
Say again, Emily.
Like why you put the particles moving to the left. Like why would it be to the
Oh, gotcha. 2 reasons. I'm going to get you to answer a series of questions, then I think it will really click. Here's time 1. At time 1, the y-coordinate of that dot tells me where the particle is. So based on this scale, that's about -5. So I'm about, I have to compress my scale, but I'm like here. Okay with that? When I go to time 2, the y-coordinate's about negative, oh, time 2's over here, sorry. Time 2 about negative 30. So where would I be if I'm the particle? So I'm moving along this line. These blue dots tell me where I am located at different times. So time equal 1, I'm at 5. The center's right here, that's 0. So here I am at negative 5. At time equal 2, I'm now located at negative 30. So where would I be?
Would you just be at 30 or?
I'd be at 30, which would be way over here, because it's negative 30. Does that make any sense?
Yeah.
So that's how I know I'm moving left. Because I pay attention to these y-coordinates, and I see these y-coordinates becoming more and more negative. So as you read the graph, this is time elapsing.
Oh, I see it.
You see it better?
Yeah.
3 points. Please, Andrew.
So it's talking about the fact that the particle position is decreases from 0 to 4.48. But what about before 0? Is it still decreasing then, even though it's positive?
It is. 3 points. Look up. It's exactly the same idea, different numbers. Here my position is very, very positive, which means at that time I would be way over there. But as time elapses, as I read the graph, my position becomes, let's see, positive 60. I moved this way to get there. Now my position is positive 40, positive 20. I am moving this way, for sure. Anyone else? Please.
So I think you had a better way to show it, because when someone is talking about how they don't really understand when it's moving left, one thing you can do is just maybe turn the graph to the side like this, and then just say it's moving left if you look at it a different way.
I have to check it. I've never tried that.
When it's going on the negative downside or whatever, it just looks like it's going left if you just turn it.
Make another packet for the next poor person who doesn't get one. Yeah, you can think of it that way if that helps. So, points for Cameron. Anybody else? Please, Ainsley.
So you said on the test, we're just gonna get one equation, one of the equations, and we're just gonna have to memorize the charts, figure the other things out. That's it? Okay.
No, it's perfect. Look at me. 2 more for Ainsley. A very common AP question is, they only give you the velocity graph. So you don't see the other 2, but they still ask the same question. During what time period is the particle moving to the left? Look at the orange graph. Notice that the entire time that the blue graph ties into what Andrea said, again, you get points every time I say your name, the blue graph's going down for quite a while. That means the particle is moving left for that entire time period. The entire time during which the blue graph is going down, the particle is going left, every single y-coordinate on the velocity graph is negative. All of these y-coordinates of the velocity graph are negative. They correspond perfectly to the blue graph's behavior. That's what the chart summarizes. Is that what you meant?
Yeah, that's
Perfect. 2 more. Please, Taylor.
So as you're with the velocity graph, you were saying oh, it's coming, so it's negative 30, and then it's negative 50, and so it's speeding 50. But it's also the acceleration is positive, and then the velocity is increasing, right?
If the acceleration is positive, the velocity is definitely increasing. Keep
But
going.
at time equals 0, the velocity is -1, and the acceleration is positive, but if you go to 0.1, the velocity is getting closer to 0, so it should be slowing down, but the acceleration is still positive.
Everyone listen really close to her question. Full ticket for this one. Listen close. What Kayla stumbled across, and the way you asked the question was really well stated, is don't forget, we talked just a little bit about it in the gold packet. Speed and velocity are not identical. they're similar but different. So as the velocity changes from -1 to say -0.5, the speed changes from 1 to 0.5. So the particle is slowing, but mathematically the velocity is increasing, which seems weird, because the velocity went from -1 to -0.5. That's a mathematical increase in the velocity, but it's actually a decrease in the speed. Does that help at all?
Okay, yeah.
So the acceleration and the velocity correspond perfectly by this relationship, Danika's chart, but don't throw speed into it. It doesn't fit anywhere here necessarily. Is that okay? Two more. Let's go, Andrea.
But isn't, so if it's 0.5 or -0.5, isn't that still less than -1?
It somewhat depends on how we think of it. So everyone look here, 3 for Andrea. In this chart, and on any AP question, when they say increasing, here are examples of increasing. -10, -5, -1. That's increasing mathematically. 5, 10, 15, that's increasing mathematically. So that's what they mean by increasing.
Okay, so basically just
Going up, on the graph, going up. So the velocity here, definitely increasing, but as Kayla said, the speed definitely decreasing. Yep, that's how they're going to try and trick them, for sure. Questions? Awesome. One other thing to note over here on Danika's chart. Okay, when you read a graph, time is just elapsing as you read the graph. As you go across the graph, time is ticking by. It's elapsing. So the items in the chart are not talking about the x coordinates that you look at. The items in the chart are referring to the y coordinates really. Like we just kind of, time just happens as we read the graph. But these increase, I mean, the x coordinate is involved, but it seems to help students more to just focus on the y values. If the y values are going up, we say the graph is increasing. If the y values are positive, the y values, not the x values. So the chart's all about the y values. Question. Keep going. Next one. Okay, the position graph is increasing. And again, we're just reading the graph from left to right. So we just got done discussing how the position graph is decreasing from time equals 0 until time equal 4.848. So now it just continues on. This is kind of like what Nick was asking about. So now we just note that from time 4.848 to 7, you notice they stopped at 7 is because you got to stop the graph somewhere. It keeps going. The position graph is increasing. Questions? So now it says, therefore the velocity graph is, and again, this is not meant to be hard, but I think you learn better if you say it versus I say it. So raise your hand if you know what goes in this blank right here. Don't overthink it. It's not supposed to be hard. Allie? Positive. Right here. When the position graph is increasing, when the y coordinates of position go up, the y coordinates of velocity must be positive. And if I look at the graph, and you should as you're doing your homework, make sure that the correspondence makes sense to you. So I see here my position's going up, and during that entire time period, the y coordinates on the velocity graph, every one of these y coordinates is positive. A note to Mr. Recti, this board is interesting because it's touch sensitive.
Oh.
You stand too close, the pen stops working. Because it thinks you're trying to touch somewhere else.
That's funny.
It's good and bad, you know. How many got it? Show me. Hands. 2 points, 3 for all. Question. Cool. New definition. So on that white reference sheet, on the side that I pointed out that had this side here with the box at the top, I've simply reprinted a couple of those definitions to make it easier for us to talk about them. Okay, it says here, any function. So what you've got to learn to do is apply this definition to any of the functions. In this particular case, we're going to apply the definition to position. But it applies to any. So, the position has a relative or local max. You must learn both words. They will test you on both. You never know which one they're going to use. So the position has a relative or local max when that same function, so when the position changes increase to decrease. Now, I did not include the definition for local min. I figured you're all smart enough to know it's just the opposite. So that's what we're looking at right here. The velocity graph, the position graph changed from decrease, right here. Position graph is decreasing. Now the position graph is increasing. When that change occurred, the position graph has a relative. You can abbreviate relative, that's allowed on the AP test. Or local minimum in this case at that same time. So that's just introducing you to that idea, which I think you actually learned last year as well. So, questions? Awesome. Here's the most important part right here. Because they don't typically test you on the first half of that definition. They more heavily test you on the second half of that definition. So any function, in this case position, any function has a local max when that same function changes increase to decrease, or when that function's derivative. So we talked earlier today, and on the gold packet, velocity is the derivative of position. So the position has a relative or local max when the velocity changes positive to negative, meaning the y-coordinates of the velocity change positive to negative. We see that happening. That's why I drew these dotted lines. Right here, when the position graph is changing decrease to increase, that's the exact same moment in time when my velocity y-coordinates are changing from being negative y-coordinates to being positive y-coordinates. It's exactly the same time. So that's why I messed up. Apologies. I jumped to the wrong thing. That is important to notice. That was a mistake on me. The next question is slightly different. So pause for a moment. Any question about what I just described here? And then I misread the question. The question is talking about this definition, because it's going back to position. It says, therefore, the position graph has a critical point at that same time. And then I've reprinted for you here the definition of critical point. Any function, in this case position, has a critical point when the tangent slope of that function. So right here, we talked about tangent slope last time. Right here on the position graph, the tangent slope has a slope of 0 because the tangent is horizontal. So when the tangent slope is 0, meaning tangent that's horizontal or undefined, that's when any function will have a critical point. So the position has a critical point at that time. Then we keep reading the definition. Or when that function's derivative has a y value of 0. Notice the correspondence again. Right here, the y value is 0 on the velocity graph. So this becomes v of that same time. That has to equal 0. That's a critical point. Questions? Please, Thomas.
Would it make sense instead of putting V 4.848, would I put X with the apostrophe, like the derivative?
Oh. Absolutely correct, because
Because like that's what they were looking for in the first place.
V of t is exactly the same thing as x prime of t. There's no difference. So that is absolutely correct. You could write x prime of 4.848. The answer in the back will say this, but either one is correct. 2 points. Question. And then the point I made earlier is still valid. They don't typically show you a graph of position like this and say, tell me where the critical points of position are. More commonly, they show you a graph of velocity. This is where you have to read really carefully. They show you a graph of velocity and say, where does position have a critical point? And so you have to remember this part of the definition. I'm going to go find where position has a critical point by identifying where position's derivative has a value of 0. So I look at my velocity graph and say, yep, right there. That's not where velocity has a critical point. That's the time where position has a critical point. Questions? Please.
So what is the time, how are we going to time for velocity when velocity has a critical point and not position?
Awesome. 3 points for Ainsley. I'm going to give the whole room points for this. Ainsley asked the question, at what time would velocity have critical points? Talk to each other, raise your hand. There's 2 of them. What are the 2 times where velocity has critical points? Good job. Well, listen, Ainsley, nicely done. Yeah.
Okay, just ask you.
No, I tell you, this class is all about, you can feel it. Like when it makes sense, your brain goes, I got it.
Yeah.
When you don't have it, your brain didn't just pause naturally and go, I'm not sure I understand that. Like you learn to trust that feeling, you can learn anything.
Yeah.
Because now you've stopped just trying to memorize stuff. You're like, no, I get it. Oh yeah, you can feel it. Hands up. Oh, sorry, Ainsley.
I just feel like it's going to be a lot harder when we only have one of them. But you just have to remember.
Yeah, you just remember the relationship. Hands up, hands up. What are the times where velocity has critical points? Charlie. So what times are those in this example? You're good. No worries, 2 points for Charlie. Nick.
It's x equals 0.202.
Let's pause there for 1 second, Nick. So here's what everyone needs to be seeing. At this time, you need to observe 2 things. 1, the velocity graph goes like this. So right at that time, the tangent slope of the orange, the velocity, that tangent slope will be 0. Meaning, this is where you just have to be precise. The velocity has a critical point at that moment. That's exactly the same time when the red graph, the acceleration, that red, come on, red. So the red graph, the acceleration, has a value of 0. And that's what the definition says. If you read the definition, you would say, velocity has a critical point when the tangent slope of the velocity is 0. Or when the acceleration has a y value of 0. Both are occurring at this time. The acceleration has a y value of 0. The velocity has a tangent slope of 0. That is absolutely a critical point for velocity, not acceleration.
Will the acceleration always equal 0 when the velocity has a critical point?
Always. Or undefined. Or undefined. So when the velocity has a critical point, the definition says the derivative of velocity, which is acceleration, will have to have a y value of 0 or undefined.
Yeah, I just wasn't sure because it says or instead of and.
Oh, gotcha. Maybe my bad as far as how I typed the definition. What I was trying to get you to see is you can identify the critical point of velocity in one of two ways. Does that make sense? Yeah, I get your question. That's very good. 3 points. Please.
What would it look like if it was undefined?
If the acceleration is undefined, there will not be a dot. There'll be an open circle indicating a missing point. That's what the acceleration would look like. We'll worry about what the velocity would look like later. So 2 points. Please, Alan.
An acceleration at a critical point?
Yes. It would occur right here because this is the spot where the tangent slope of the acceleration is 0. So that's a critical point on the acceleration graph. If we were to go find the derivative of acceleration, for which we don't give a name in this class, it's just the derivative of acceleration, we'd call it A prime, is one way to call that. That graph would have a y-coordinate of 0 right here. So I don't know exactly what that green graph, well actually I do. The green graph's going to look something like that. So A prime is that green graph, roughly, and it would have a y-coordinate of 0 right there. Is that your question? 2 more. Anyone else? Please.
Why is there not like 2 for the velocity graph? Like why can't it be 3.298 also? Because isn't there a critical point, right? Like at -40 or something?
No, absolutely. I simply got so excited about that one, I stopped talking about that one.
Oh, so there is.
Oh, no, it's perfect. Sorry, Emily, it's perfect. Yeah, that's the second critical point on the graph of velocity. How many knew that one? Show me that. 2 points, 3 for Emily. Anybody else? Okay, next thing. Okay, this one said, this is back to Nick's question, another point for him. Kind of like, how do I know what I'm supposed to be looking at? The velocity graph is increasing from time equals 0. Again, we just start at the beginning, time equals 0. And the other day we zoomed in so we could see it better. So here's velocity increasing. Velocity stops increasing right there. So that's why I wrote 0.202. Questions so far? Now I look at my chart to see what correspondence do they want me to see. From Danika's chart, I know when velocity is increasing, acceleration is positive. And I want to make sure it's making sense to me, so I look at the graph and go, yeah, I got it. Here's velocity going up. And another point for Kayla. Kayla saw it earlier. There's 2. All the acceleration values are positive. For that same time period, exactly. Question? Please do.
Kind of like not totally related, but on the exam today, it was points for spelling.
No.
Okay. Like if
Yeah.
it's close enough, then it's like.
Yeah, they're actually very forgiving of
Okay,
that one.
good.
Yeah, you're good on that. No, they don't care about grammar. They don't care about spelling. They do care about correct mathematical notation, so I'll keep pushing you for that one. They allow certain abbreviations. So what I try to do is all year long I try to use what abbreviations are allowed, so you just get used to it. And if you see me writing something out, you're like, oh, okay, they must not allow the abbreviation, so I write it out. Or I'm uncertain, so better to be safe than sorry,
Yeah.
as said. Next one, number 4. Number 4, I'm going to let you do at home by yourself. We've already covered those topics. So let's move on from there. Number 5 has got something a little new. It says the acceleration graph is blank from time equals 0 to time equal what? So I look over here at acceleration, and I notice from time 0, my guess is they're talking about decreasing here. So acceleration graph is decreasing from time equals 0 until time equal 1.75. Questions? So Nick gets another one. That's why you should raise your hand and end up mentioning your name a lot, especially if you do it early in the class. When acceleration is decreasing, the velocity graph must be concave down. For that same time period. And I believe you discussed concavity in a previous class. So here's a common misconception. Please memorize this. This shape, or any part of that shape, represents a curve that is concave down. The curve does not have to have the complete upside down curvature to be concave down. If the curve looks like this, that curve is concave down. The curve looks like this, that curve is concave down. Question. Some people think it has to do both. It does not.
So at time equals 4.848, would that mean it would be concave up now?
For which color?
I was looking at the position right now.
Either way, just
Okay.
keep going with your question. I'm not sure.
Well, would it be concave up now, or?
Let's go to the next slide. It'll help answer your question. 2 points for Janessa. So let's go to number 6. The acceleration graph is, we just saw that acceleration was decreasing initially. So we saw acceleration decreasing until 1.750. Now acceleration is increasing for the rest of the time. So here the acceleration graph is going to be increasing 1.750 to 7 seconds. Look over here. Therefore, the velocity graph must be concave up for that time period. And I think this is Janessa's question, another point for her. Look at velocity. Remember what I talked about. When acceleration was decreasing, so here's acceleration decreasing. During the entire time that acceleration is decreasing, the velocity graph must have a concave down curvature, and velocity does. This section right here is definitely concave down for velocity. At the exact moment when acceleration starts to increase, right here, that's the exact moment when the curvature of velocity changes to concave up. So now velocity is concave up. Velocity will remain concave up for the rest of the graph because the acceleration remains increasing for the rest of the graph. Is that what you meant?
Yeah.
2 more. Please.
How do you know it is looking for acceleration increasing? Because couldn't you also say acceleration is positive from like 3.298 to 7 seconds?
Absolutely.
Like, how do you know it wants the increasing amount of positive?
No, perfect, Timmy. 2 points. Basically, the only way you can tell is by reading a subsequent statement and saying, oh, wait a minute. Number 6 is trying to get me to understand how these two things correlate to each other, correspond. So the only reason I knew that is by looking here, looking at, okay, they're talking about acceleration, and then they're going to ask me how it corresponds to the velocity being concave something. So I go, oh, I got it now. The velocity's concavity corresponds to the acceleration increasing or decreasing. That's the only way to
But
know.
if it's looking for a velocity increasing and decreasing, you're looking for a positive or negative acceleration.
Perfect. Does that make sense?
Yeah, that makes sense.
Yeah. And they won't do that kind of thing to you on the AP test. This is just my way of introducing some way to get you thinking about how they correspond.
Okay.
Does that make sense?
Yeah.
Perfect. 3 points for Timmy. Don't leave. The bell's going to ring in 10 seconds. Look at me. We actually got plenty far in the packet for you to finish. The only term we didn't discuss specifically, but the definition is there in your notes, is inflection point. It's a really simple definition. It's just where the function changes concavity. And we were just about ready to say that, and we just kind of ran out of time. So finish the purple, and we'll check that one with you on Monday. So good work. Good job. Well done.